So it's my first presentation seated. Um, yeah, I am. Hi everyone, and welcome. I am Yassine Hamdi, PhD student here at Imperial, and it's a joint work with Aaron Wagner from Cornell and my supervisor Denis Kunduz. So we're going to be talking about lossy compression and rate-distortion theory approach. When talking about lossy compression, think of JPEG. You can compress an image as much as you want. You can choose a parameter, a threshold. But if you compress too much, then you get blurriness usually, or some artifacts. But recently, since 2017, a new approach inspired from generative modeling brought amazingly looking compressed images. So even if you compress a lot, you still get great visual quality. In particular, this is an algorithm from Google using generative adversarial networks. Now, of course, there is no free lunch. So if we get amazing visual quality, we have to sacrifice on the distance to the original image, meaning we have to introduce details or colors that were not actually there at the beginning. So this is kind of empirically verified in the other graph, where you see that, so in the x-axis you have distortion, which is kind of distance to the original image. And in the y-axis you have some measure of realism or visual quality. And we see that if you want to reduce distortion, going to the left, we have to sacrifice in terms of realism, I mean, going upwards, and vice versa. So there is this trade-off, meaning that there is somewhere some Pareto curve, and the Pareto curve is what I'm going to call the optimal trade-off, essentially. And so because of the success of this generative modeling approach, a method called formalism was proposed. And so the main new thing is going to be like the inequality in 2, but I will now explain everything. So, okay, so we have a compressor and a decompressor. And in the middle, you have the message or the compressed file, which this just means that it has NR bits. So the exponent is the number of bits. And what I will look at in this talk is a source, xn, that's actually, so xn just means a sequence of length n. So it's a discrete sequence of length n. And it's going to be IID from a certain distribution. And why consider IID? So first, this is a typical channel information theory approach, but actually it's been shown in traditional like rate-distortion theory, when you don't care about visual quality, that the, let's say, optimal trade-off for an IID sequence, a very long IID sequence, is actually nearly the same as for any actually distribution without any IID assumption. There is this essentially negligible log factor, log term, sorry, that we can forget about. In this work where we could take into account realism, I don't know if this still holds, but the hope is that studying an IID source will give good insights about the general case. So the first constraint here is the typical rate-distortion theory constraint. So it's called the distortion constraint. So we care about the reconstruction or compressed image being close to the original image. So here because it's a sequence, we're going to take x1 and y1, then x2 and y2, etc. And now the second constraint is the realism constraint, so-called, or perceptual quality constraint. And the idea there was that we want to match distributions. So we want our compressed images, when you sample a lot of them, meaning when you compress a lot of input images and get a lot of reconstructions or compressed images, we want the distribution of compressed images or reconstructions to be close to the distribution of the source. And here, D is a divergence, and so you measure the distance between probability distributions. This is a typical idea in generative modeling, that we want to match distributions. And I think the most intuitive case is when this constant capital pi is 0, so you really want to match the distributions. I'll be using the total variation distance, but our results work for general, for many other choices. So now the question is, okay, who said that this is the right way to measure visual quality or realism? Especially here we don't care about a single compressed image and about its visual quality, but we talk about the distribution of compressed images. And what we believe is actually that imposing distribution matching in this way is, yes, imposing maybe realism, but it's imposing much more than just that. So as I said, it imposes some form of generative modeling performance. And the question is then, do we really need our compressor and decompressor to act as a great generative model? This is essentially what is required. And second thing, maybe in other words, do we really need to be able to fool the best mathematical hypothesis test between these two distributions? Because we know that this performance is directly related to the total variation distance. So do we really need all of that? And why do we ask these questions? It's because we are doing lossy compression. So the whole point is to optimize resources, in particular the compression rate or the file size. So if we go and add unnecessary restrictions or constraints, we're going to pay in terms of compression rate, meaning we will need larger file sizes for no reason, essentially. So this is what our work is about. We want to model realism, put the right constraint that imposes realism and nothing additional, nothing unnecessary. And then we characterize the optimal trade-off with this new constraint. And perhaps more importantly, it turns out that our approach also gives great insight about what the divergence-based constraint was actually doing. And so hopefully in the end, you will see what this is about. So there will be a slide at some point where I will put all the mathematical, like our formalism properly defined. This will come in 10 minutes. So for now, I'm just going to lead there slowly. So I just want to first emphasize what I mean with extra resources that we have to pay to satisfy the divergence-based constraint or the distribution matching constraint. So under that constraint, theory shows that actually to get optimal compression, so optimal trade-off, you need common randomness between the encoder and the decoder, or the compressor and the decompressor, which it might seem a bit weird, but there are some setups where you can get that, for example, in federated learning or things like that. But the point is not just that you need common randomness to get the optimal trade-off, but theory shows that you need an enormous amount of common randomness to get the optimal trade-off. So, for example, theory says that for the presence of common randomness to be at all useful, for it to at least allow a 1% saving in compression rates, you need essentially the rate of common randomness to be at least 1% of the compression rate. So when I say rate of common randomness, you can see in the diagram, the variable j is the common randomness. And essentially, it can take 2 to the n RC distinct values. And RC is going to be the rate. So it might not seem big, but 1% of the compression rates is actually enormous. So let me give you an example. If the compressed file is 10 kilobytes, so NR is 10 kilobytes, then the number of distinct values the common randomness should take, 2 to the NRC, should be at least 2 to the 800 distinct values. And of course, this is an enormous disconnect with practice, because in implementations with Python or PyTorch, you take a pseudo-random number generator, and usually what they will have is not more than 2 to the 64 distinct values possible, which is, so 2 to the 64 is nowhere near 2 to the 800. So there is a kind of impractical or unrealistic demand for common randomness, for an enormous amount of common randomness, just to get a 1% improvement of compression rate. We're not even talking about getting the optimal compression rate. Meaning if we don't have this common randomness, then we will severely pay in terms of compression rate. We will have bigger file sizes, all that to satisfy the divergence-based constraint. And we see in state-of-the-art image compression algorithms, they're not using common randomness, and certainly not these enormous amounts. So, okay, so that being said, okay, what is the correct or better version definition for realism or formalism for realism? And if we're not going to talk about the distribution of the compressed images or reconstructions, we're going to actually talk about single realizations. Think about that, it's quite natural. We can take an image and say whether it looks realistic or not. And actually, the answer can be found in algorithmic information theory. And that part, the fact that we should look at algorithmic information theory, is not a contribution of mine. It's Lucas Tice from Google who found that, or who, it's more like people from the machine vision community were not aware, and he brought that idea into the machine vision community. So the question that was asked in algorithm in the literature is, does a sample Y, oh, there is an echo, I guess. Okay, no, it's okay. So the question is, does a sample Y, think of a compressed image, does a sample Y look like it comes from a given distribution P, which would be the source image? Does a reconstruction image look realistically like a sample from the source distribution? And the answer is that actually many different authors essentially converge to nearly the same formalism, and it is the one here. So when I say nearly the same, it means like as usual, there are log terms that we neglect, like in Kolmogorov complexity, etc. So let's look at this a bit in detail. So as I said, we have a reconstruction. Again, it's sequence with the source was a sequence, the reconstruction is a sequence, yn. And we want to tell whether this reconstruction looks like a realistic sample from the source distribution, which is IIDP. And essentially the consensus is that the notion of realism is encompassed by the values of log-Lacock ratio. So precisely, you have inside this set functions or scoring functions that take a sequence yn and give a score, which is a real number, a log-Lacock ratio, where in the denominator you have the target distribution, which is here IDP, the source distribution, and in the numerator you have some measure. And this is essentially the set of all log-Lacock ratios, in the sense that the numerator can be not necessarily a distribution, but can be actually broader than that. The sum of weights can be less or equal to 1. And Qn and this IDPN should have the same support, essentially. So it's a set of all log-Lacock ratios with a constraint that they be lower semi-computable. That's an important constraint. Okay, so again, the point is that the notion of realism is encompassed by the values given by these log-Lacock ratios. If you know a bit about hypothesis testing, you might see that this is log-Lacock ratios are what we use in hypothesis testing, but I will not expand on this. Okay, so now just a few words about this set of, I will call them critics, in the sense that they take a reconstruction or a compressed, think of an image, and give a score of whether they look realistic or not. So yes, it turns out, and that is one of the greatest successes of the theory, is that there is one log-Lacock ratio which is the best scoring function for realism. In some sense, it is more sensitive to realism than any of the others. I might say a few words about this a bit later. So now that we know how can we characterize realism, or how can we measure realism, now we want to bring that to lossy compression, and that's where my contribution starts. So before everything, I will just give you a bit more of intuition about these scoring functions. So I just want to emphasize that lower semi-computability, I don't know if everyone is aware what it is. It's actually not a very difficult thing to check in a theoretical work. There are very good lemmas that tell you that basic functions are lower semi-computable, and then sums and products of them, etc. So a lot of it's quite easy actually to go and check that. Even for very complicated operations. Okay, so most basic scoring function for sequences is computing a frequency. Thank you very much. So we want to compute the frequency of a pattern appearing in the sequence. So X is a pattern of interest. Here it's a single symbol, but you can actually do it for any pattern of any length. And so Sx of Yn is the number of occurrences of X in Yn. And from the number of occurrences, we're going to look at the frequency. And what I'm saying is that there exists a logarithmic ratio in that set, which is going to essentially be sensitive to the frequency of pattern X. Precisely for any sequence of random variables Yn, if the frequency of pattern X doesn't converge to what we would expect, which is the probability of X, in some sense, then essentially the score will explode. The expectation of the score will not be bounded as n goes to infinity. So this is the first thing we can do with log-log ratios, but we can even do more. And I think that's the most important thing is testing frequency is nice, but it's kind of a weak thing to look at. But we actually care about the order of symbols in the sequence. So some sort of not joint distribution, but something like that. So I'll take sequences of zeros and ones to make it simple. And N1 is going to count the longest run of ones in the sequence. So longest sequence of consecutive ones which appear in the long sequence Yn. And we know what we would expect according to the distribution of the source. It's this expectation of N1 of Xn. And now, essentially, this says is that if N1 of Yn, the longest run length, is not essentially very, very close to the expected value, the log-log ratio that I didn't show here, but there is a log-log ratio which will essentially spot that, and the score will explode again. So we can test for frequency, we can test for longest run of ones, we can test for actually many things. And it goes beyond these simple operations. We know that we can construct something involving Kolmogorov complexity, which is not just about frequency and not just about the longest run of ones. It's much more than that. So log-log ratios look like they're very, very niche and special, but actually you can do pretty much anything. Now let's start our formulation. So the nice thing is that we're not just going to have a formulation where we test the realism of a single reconstruction or think about a compressed image, but we're going to do something a bit larger. In particular, we noticed that with log-log ratios, we can also do, if you give a lot of samples to the function delta, to the log-log ratio, then you can approximate essentially a divergence. What I mean by that is very simple. With a lot of samples, you just approximate the distribution, and then you just plug in to the divergence. Very simple estimator. So you can do that with a log-log ratio. And so the idea is that if the score doesn't explode, we're good. If not, then the divergence constraint will not be satisfied. So now our formalism. So first, I didn't tell you what I meant by samples. So what do I mean by get samples? So it's actually pretty natural, I think. You first sample a lot of items that you want to compress. So IID from the source distribution. So each of them is a sequence, as I said. So then you take X1, you compress it, decompress it, you get Y1. And then completely independently, you take x2, compress it, decompress it, take y2. So you get these tuples xk, yk, which I call samples from the compression scheme we want to study. And to talk about now the performance of this compression scheme, we look at these samples and we look at the following things. Again, distortion. So it's actually the same expression, except that we average now over k, so we average over the batch of samples. So we look at x1, y1, then x2, y2, etc. So this is not very new. But now the main point is how we define realism, or what is our constraint for realism. Again, inspired from previous examples, we want the score not to explode. And now I allow there to be a single sample, but I also allow, and we'll see why this is useful, more samples than just one. And the main point is that I want this constraint to be very strong, in the sense that I ask that for every log-likelihood ratio in the class, every lowest semi-computable log-likelihood ratio, the score given by that log-likelihood ratio applied to the samples doesn't explode for every one of them. And okay, this I think needs it will take time maybe for this to sink in, so I will keep this a constraint in all the following slides, so you will have time, don't worry, to look at it. And so just a few comments. This is principled in the sense that we know the notion of realism is encompassed by the values of the log-likelihood ratios. So by looking at all of them, we hope this captures realism. The specific form of having a score that doesn't explode, first it comes from, you can see it in the examples I gave, but actually very much inspired from algorithmic information literature about the kind of typical size we want for the score, essentially. And so this includes all notions of like testing for frequency. So the frequency is going to be correct for any pattern you want if you satisfy this constraint. The longest run of ones will be normal in a sense. It will not be too short, not too long in expectation, and much more than that. Now you might, again, as I said, you could just look at a single sample. I think it's the most natural thing to do. Take a single image and look at its realism. But you could actually choose the number of samples you give to the critic. And this will give you different levels of difficulty or more stringent notions of realisms as you add samples to them. So this will become clear in our coding theorems. And this is our main result, that actually, if the number of samples you give to the critic is not impractically large, meaning precisely if it's not exponential in the length of the sequence, so in n, then deterministic schemes are optimal to reach the optimal trade-off between compression, distortion, and realism. And so we don't need any common randomness, especially not large amounts. And deterministic codes are enough, although what we're requiring is pretty stringent, I would say, because we're asking that this score be bounded for every log-likelihood ratio. And this explains the gap between the state-of-the-art image compression algorithms and the theory, because they're not using common randomness. And this kind of explains why you can still get great realism without need for common randomness. I must maybe admit that this is an asymptotic result. So that means that maybe what I would expect is a result like in the general case, it might be useful to have a little bit of randomness, but certainly not enormous amounts of randomness like the theory is predicting. And we will just see maybe a bit more insight about this. So as I said about the divergence-based constraints being equivalent to a bounded log-likelihood ratio if you give enough samples, we have this result that says that if you give an insanely large number of samples to a critic, then our constraint is actually just equivalent to having the distributions match between the reconstruction and the source. So we recover exactly the same divergence-based constraint. So total distance going to 0, meaning that our formalism becomes the same as what was done before. So we get the same role of common randomness, the same needs for enormous amounts of common randomness if we give this enormous amount of samples to the critic. So kind of what this says is that, okay, the initial idea that, okay, let's look at the distribution of reconstructions and let's make it match the distribution of a source. This was indeed measuring realism because it was indeed equivalent to our constraint here, where you look at all logarithmic ratios, so you know that this kind of encompasses the notion of realism. But realism of what? Realism of an extremely large ensemble or set of samples. So it's a joint realism of a very, very large set of samples. And I believe that this is not the right way to measure realism, just because it's not even practical. Like intuitively, an exponential number of samples is not even practical. So any human observer essentially, and this is a bit the intuitive part, any human observer will not go and look at jointly at an exponential number of samples. And so to conclude, what we propose are constraints which can be used for a single reconstruction, to judge a single reconstruction or a bit more than that, explains the the discrepancy with practical algorithms. Again, just interesting to know for further applications in broader machine learning applications involving realism, that realism is encompassed by essentially logarithmic ratios, and in particular the best one, the one which is the most sensitive to realism, which is linked to Solomonov prior action. And we don't need to have a great generative model. We don't need to be able to fool the best mathematical hypothesis test to get realism. And something also, maybe an insight, is it really matters when you go and measure realism. It really matters how many samples you take at a time to measure realism. So if you measure realism of a bunch of samples jointly, and you look at correlations, etc., if you give an enormous amount of samples, then your notion of realism, your metric, is measuring something that is much different than what people usually do in practice, where they look at maybe 10,000 or 100,000 samples only. So that's kind of all for me, and thank you for your attention.